Welcome back, students. In this section, you will learn about the excitation-contraction coupling of the skeletal muscle. So, to understand the excitation-contraction coupling, you need to know basics of structure of the skeletal muscle, sarcomere, neuromuscular junction, how the action potential is generated. So, in this section, you will learn about changes in muscle during contraction, molecular mechanisms of cross-bridge action, walk-along theory of muscle contraction, sliding filament theory of muscle contraction, and types of muscle actions. So, to begin with excitation contraction coupling, what is it? So, excitation contraction coupling is a physiological process that links excitation leading to contraction of the skeletal muscle. So, to give a brief review of whatever you studied in the previous sections. So, remember, muscles contains bundles of muscle fibers called fasciculi. So each muscle fiber contains hundreds and thousands of myofibrils. So these myofibrils are formed by the myofilaments. We have the actin and myosin myofilaments, which contracts and which interacts and contraction happens. Now this is the myofibril, and this is sarcomere, one section of the myofibril. So sarcomere extends from between two Z lines or Z disc it is called. So you have the actin filaments, thin actin filaments and the thick myosin filaments which partially interdigitate. So it is due to their interaction, contraction happens. So this is a cut section of the muscle fiber. So you can see the sarcoplasm here. In that you have myofibrils, hundreds and thousands of myofibrils. So in the sarcoplasm, other than myofibrils, there are nuclei, mitochondria, etc. And then you have the T tubules. So T tubules, they run transverse to the myofibrils, to the inner part of the myofibrils, which can propagate the impulses, the action potential to the inner of the muscle fiber. And then you have the longitudinal sarcoplasmic reticulum, which stores a lot of calcium, and the calcium which is released from the sarcoplasmic reticulum is responsible for the interaction between actin and myosin. So this T tubules, on the other side you have dilated cisternae of the sarcoplasmic reticulum. So all three together is called the triad. So this constitutes a sarcotubular system. So as you know, the muscle fibers are innervated by the motor neurons. So the end of which is called the neuromuscular junction. So in the axonal terminal membrane, you have the acetylcholine, which is a neurotransmitter. So it is stored there. So once the action potential reaches the end of the axons, what happens? There is release of the acetylcholine into the synapse, which will go and bind to the voltage gated sodium channel. There will be increase in the influx of sodium, leading to depolarization of the motor end plate. So there is initiation of action potential with that. So this action potential excites the muscles. So that is excitation, and this excitation has to result in contraction by the interaction between actin and myosin. So that it will lead to contraction. So let's know in detail about the excitation contraction coupling. So as I've told you, the neuromuscular junction, acetylcholine is released. There is influx of sodium. There is a depolarization, and there will be initiation of the action potential. The action potential is propagated through the T tubules into the sarcoplasm. So in this membrane, you have the DHP receptors. It's a calcium channel, voltage gated calcium channel. So when the action potential is propagated, there is opening up of the DHP receptor leading to release of calcium. And this DHP receptor is communicating a signal to the something called the ryanodine receptor, which is embedded in the sarcoplasmic reticulum here. So this is the sarcoplasmic reticulum. So you have the ryanodine receptors, which is embedded in the sarcoplasmic reticulum. So they are calcium release channels. So they will release the calcium from the sarcoplasmic reticulum into the cytoplasm, which will produce increase in the intracellular calcium. So here you have the DHP receptor when stimulated, when opened, it will communicate a signal to the ryanodine receptors on the sarcoplasmic reticulum, leading to the increased release of calcium. So calcium is increased in the cytoplasm. So intracellular calcium is increased, which will cause the interaction between actin and myosin. So this actin and myosin, they interact and produce contraction of the skeletal muscle. So what happens during contraction? So here you can see the relaxed muscles. So this is sarcomere. So from one Z line to other Z line, you have the thin and thick filaments, actin and myosin filaments. They interact, they pull together so that the two Z lines come together from here to here, from here to here. It's going inside. They are coming closer, and the H band, this is the H band in the middle section, disappears, and the I band is also decreased. So when the muscle is contracted, what happens is there is sarcomere contraction or shortening. So sarcomere segments which is repeated throughout on the myofibrils, so that will cause the muscle to contract. So this is the sarcomere two-dimensional structure. So this is the myosin in the middle and the actin. These are thin filaments. Actin is thin filament and myosin is thick filament. If you zoom in, you can see actin is a structure which contains actin and troponin. Okay, so troponin has three subunits. We have troponin I, which binds to actin, troponin C, which binds to calcium, and troponin T, which binds to tropomyosin. And then you have another protein which is called tropomyosin, which is blocking the active site on the actin. It's a double helical structure containing actin, troponin, and tropomyosin, of which tropomyosin is blocking the active site of calcium. Now, this is the myosin molecule, thick molecule. So it has a tail, it has a neck or the hinge area, and it has a head. So head has actin binding site, which is the head which goes and binds to the actin, and it has myosin ATPase enzyme activity, and it can also bind to ATPase. So for the cross bridge action, you need ATPase, sorry, you need ATP, which provides the energy for the interaction. Okay, so here what you can see is the contraction cycle begins with the arrival of calcium. So when the sarcoplasmic reticulum releases calcium, what happens? Calcium will come and bind to the actin filament. So actin filament, on that you have the troponin. We have troponin C, remember. So calcium will come and bind to the troponin C, and they will produce a structural change which will pull away the tropomyosin from its binding site on the from its active site of the actin. So tropomyosin is removed from the active site, and the active site of the actin is exposed. So once the active site is exposed, what happens? The myosin can come and bind to it. So myosin head will go and bind to the actin, exposed region of actin, and forms a cross bridge. It is called cross bridge. So you have the actin here and the myosin head you have. It will go and bind to the active site of the actin. So the next step, what it does is, after the cross bridge formation, once it binds to the active site of the actin, the head will tilt towards the tail. It will pull. When it tilts, it will pull the actin along with it. Okay, so that it is pulling the actin towards the M line in the between. Okay, so you have the Z disc in between. You have the actin, you have the myosin. It is pulling the actin towards the M line. Okay, so that is called as the power stroke, where the head is tilting. Along with that, it is pulling the actin. Okay, so once it tilts its head, it will detach, the myosin head will detach from the actin, and it will come back to its normal direction, and then it will go and bind to the another active site of the actin. So it will go to bind to the actin in the 45-degree angle, the myosin head, and it will tilt the head. Along with that, it will hold the actin. It will next go and bind to the next active site of the actin. Again, it will tilt. Again, it will release, go back. Again, go and bind to the actin. Pull, release, go back. So it is, sliding along with that actin. So myosin, after tilting, I told you it is being released from the actin side. Let's see how. So, as I've told you, the head of myosin forms the cross bridge with the actin. The head bends or tilts, leading to pulling and dragging actin. So, that is a sliding action of actin on the myosin. It is called the power stroke. The head detaches from the actin filament, and they go and bind to the next active site of the actin, attaches again, tilt and pull the actin along with. So this process continues. So it is as if the myosin head is walking along with actin, so pulling actin on the way. Okay, so that is known as walk along walk along theory of the muscle contraction. So it is like the myosin filaments are walking along with actin, step by step, pulling the actin inwards towards the M line and producing contraction of the muscle. Now, to produce contraction, the initiation trigger factor was calcium, which was released by the sarcoplasmic reticulum, and ATP is also required for the energy. So, ATP is utilized for the energy required by the power stroke or the tilting of the uh, myosin head. So, you have to understand ATP is converted to ADP and inorganic phosphate in the myosin head. After ATP goes and binds to the myosin, it is converted to ADP and inorganic phosphate, and energy is released. That energy is stored in the myosin head. Okay. So when myosin head goes and binds to the active site of actin, it has ADP and inorganic phosphate, which is bound to the head. So after it goes and binds to the myosin head goes to bind to the actin, it will tilt the head and slide the actin along with it. So during this tilting the head and sliding the actin or power stroke, this ADP along with the inorganic phosphate molecule is released. So after that it is released, the power stroke happened. Next, what happens is an ATP will come and bind to the myosin head. So this binding of the ATP to the myosin head causes detaching of the myosin head from the actin filament. It detaches. Again, what happens? This ATP is converted in the myosin head to form ADP and inorganic phosphate. After that, an energy is released, which is stored in the myosin head. So this myosin head with ADP and inorganic phosphate and the energy stored will go and bind to the next molecule of actin. Then it will tilt, sliding the actin along with it. So in this uh, step, the ADP is released, and next the ATP, another molecule of ATP will come and bind to the myosin head. So this process continues. Okay, so you need ATP for generation of energy for the power stroke. So that is required for the contraction of the muscles. So with the inverse, sliding of the actin and the myosin, so the sarcomere gets shortened and the muscle contracts. So here the excitation got coupled to the contraction. So it's called as excitation contraction coupling. And this is a sliding filament theory where myosin is making the actin slide towards the M line. So these contractions can continue as long as calcium is high in the sarcoplasm. So what happens when the action potential stops? So there is muscle repolarization leading to the calcium channels going to close. So once the calcium channel close, the calcium current inwards will stop. There is an ATP pump in the sarcoplasmic reticulum which is responsible for the removal of the calcium from the sarcoplasm into the sarcoplasmic reticulum. That is called as SERCA. This is SERCA in the sarcoplasmic reticulum. Okay, so it removes the calcium from the sarcoplasm. So without the cross bridge, without the calcium, the cross bridge does not form and the muscle will not contract, the muscle will relax. So calcium is required for the muscle to contract. So repeated action potential is required for the muscle to contract. So action potential will produce excitation. That excitation gets coupled with contraction and that leads to muscle contraction. So this is a summary of what we discussed today. So you can see you have the neuromuscular junction. The neurotransmitter acetylcholine is released, which will produce depolarization, that is uh, increased action potential generated at the nerve membrane, which goes inside, opens the calcium channel at the DHP receptor, which will signal the sarcoplasmic reticulum, that is the ryanodine receptor, to release the calcium, which will go and bind to the uh, actin and remove the tropomyosin from the binding site, and the myosin head can go and bind to the active site of the actin, and the myosin head can tilt the head, leading to gliding uh, mechanism or stroke. So that is called as power stroke, where the head is tilting, dragging the actin along with it. So the sarcomere shortens. So muscle contracts. Sarcomeres are segments repeated on the myofibrils. The muscle will contract. So an ATP is required for every sarcomere for contraction for the energy release. Coming to the types of muscle action or muscle contraction, there are two types. We have the isometric contraction and the isotonic contraction. In isometric contraction, when the contraction happens, the length of the muscle remains constant. Whereas in case of isotonic contraction, length of the muscle shortens, but the tone or the tension remains constant. So in case of isotonic contraction is subdivided into concentric contraction and eccentric contraction. In case of concentric contraction, the muscle is shortening under load, and in eccentric contraction, the muscle is lengthening under load. So you can see the isometric contraction here. So the contraction happens in your arm when you hold the dumbbell. So when you're holding the dumbbell, you think the muscle is not contracting. It is contracting, but the length does not shorten. So you need contraction of the muscles to hold the dumbbell, or the biceps brachii is contracted. So in case of isotonic contractions, we have the concentric. So when you're holding the dumbbell and then you flex your arm, so the contraction happening is called as concentric contraction. Okay. So the biceps brachii produces tension and shortens. Whereas in case of eccentric contractions, so when you flex your arm, it is called concentric. When you extend your arm holding a dumbbell, it is called as eccentric contraction. Okay. So there is lengthening of the muscle, that is called as eccentric contraction. Another example I can give you is while doing push-up. While doing push-up, your torso and your lower limb all are under isometric contraction. So there is no shortening of the length of the muscle. Whereas your shoulder and your arms are doing isotonic contractions. You are flexing and extending. Okay, so there is shortening of the length of the muscle. So that is isometric and isotonic contractions. So these are the summary of differences between isotonic and isometric contractions. So what you have to understand is in isotonic contraction, the tension uh, remains the same, the muscle length reduces, whereas in isometric contraction, the muscle length remains same, where the tension varies. So with this, we come to the end of this section of the video. Thank you.